Let me focus first on some pictures. They are not in the chronological order, but doesn't matter. So this is Anatoly in somewhere near Kyoto, if I understand correctly. Looking at the vegetation and landscape and his age, it must be somewhere near Kyoto. So clearly he had some Zen practice there. So this is definitely Kyoto. Although it may not be, but I think it is Kyoto. It's Nara. It could be Nara. So this is, yeah, this is Tole and Leon Takhtajan, and this must be in Kyoto, yes. So this is Omar Foda and Anatoly. So that's probably Kyoto, or maybe somewhere else. Maybe Melbourne, yes. So this is Anatoly and Sasha Veselov. Yes. So Sasha Veselov is expected to be in Beijing next spring. This must be also somewhere in Kyoto. Okay. So this is St. Petersburg. If I understand correctly, this is the year 1991. and yes. No. This is Alexei Morozov, and this is Anatoly with his beard. He was defending. Yes. Yes. This picture, thanks to Takashi Takebe. So this is Anatoly and Kharlamov, and Sonia Kharlamov. So yes, Kharlamov is a symplectic geometer. He is a student of Rochlin. He's in Strasbourg, I think. Okay. Maybe. This is Anatoly. Kyoto. This is in Sanya. This is Lasku and Anatoly. So, Lasku was a very good friend, and he is an outstanding combinatorialist. He was, yes. So this is Anatoly. This is Anatoly and I. I don't remember where this was, but by the color, it's probably Kyoto. Yes, it was another conference dedicated to Anatoly. This is Masatoshi Naomi and Anatoly on the same occasion. And this is all. So, Anatoly, happy birthday. And now we can. Yeah. Okay. So, shall I start the presentation? But how can I find it here? Is it here? This is one of the mics that you will hear my breathing. Like Darth Vader. It's okay. It will take some time, but it will work. I haven't seen a moment when it didn't work. It might take some time. So just about my presentation, there will be no combinatorics there, unfortunately, and there will be no beta ansatz. But there will be some integrable systems, and in the future, there will be some beta ansatz, and hopefully some combinatorics. Maybe some continuous combinatorics. Meanwhile, I have a question to present combinatorialists and the presentation series. So, do you, have you seen somewhere standard Young tableaus of the continuum type, where the numbers are not from 1 to n that are entries of the tableau, but some kind of continuous variables? Ah, very good. Which are continuous. Ah, pattern. Okay. Yes. So I'll talk about the current work. The text should appear very soon with Andrei Liashyk and Sechin, and it's about hybrid integrable systems. I was worried about the word hybrid, whether it's appropriate in this setting, but it turns out that it's being already used in the context of representation theory of quantum groups and groups of units. There is such a notion as hybrid quantum groups. So, Anatoly, congratulations with the birthday. So now, so they talk about it's about quantum integrable systems on a classical integrable background. So in physics, this is known as certain approximation to quantum systems when you have a quantum system with two subsystems. One subsystem is the classical one, and the other one is what? So it's known as Born-Oppenheimer approximation to describing the atoms when atoms are moving according to the classical mechanics and electrons are moving as quantum particles. So here is the mathematical framework for such systems. Actually, it may sound rather artificially mathematical in this context of Born-Oppenheimer systems, but as we will see, that is exactly what will be happening. So mathematically, such thing is the following. So we start with the classical system. So for this, we fix the phase space. That's a symplectic manifold. So the simplest one is standard symplectic space with coordinates is the coordinate. So we want to have a quantum system on the top of such classical system. So that means that we have to fix a vector bundle over our phase space. For simplicity, let's assume that this quantum degrees of freedom it's a finite dimensional space. So it's Cn, and we have a real quantum, not real but meaningless quantum system. We have to assume the Hermitian structure on each of these spaces. So we have a Hermitian structure on each fiber which smoothly depends on x. So then there is an associated bundle of simple algebras, of matrix algebras, where the fiber is the endomorphism of V. Hermitian structure on V gives the star structure on each fiber. So this is what we have. If we want to develop some kind of Heisenberg picture of quantum mechanics, we work with the associated bundle, and for the Schrödinger picture, we have the this bundle of. I mean, by some abuse, you can say that this is the space of states. Strictly speaking, a state is something that's determined by a vector. Here, it's up to U1 rotation, but nevertheless, let's just call it space of states. So, then the algebra of the space of smooth sections maps from M to endomorphisms P. This has the natural structure of an associative algebra, just with pointwise multiplication. So it has a star structure induced by the star structure of fibers, and it has a center. Center is just the algebra of functions on M times the section of the associated bundle that corresponds to identity element of each fiber. So, because M is a symplectic manifold, this center has a natural Poisson structure with this Poisson bracket, and the space of all sections of this vector bundle is a module over the naturally over this subalgebra. Moreover, it's A itself is finite dimensional over Z, just because the fibers are finite. So, but we also want A to be a module over the Poisson algebra. So we want, in other words, we want to define Poisson brackets between Z and any element of this bracket. So, we want to define the Poisson bracket central element between functions and sections of our bundle. So, that means that Poisson bracket should act by derivations of the associated multiplication, and it should act by derivations of the Lie algebra. I mean, in other words, it should be a module over the Lie algebra Poisson bracket. So it should be this property. This property reads very simple. C1 acts by derivations of this expression. So this is the Poisson bracket 1 and C2, and then this is the Poisson bracket 1. So the geometry of this situation, we studied some similar reasons with Alexander Voronov and Alan Weinstein, and it's a very simple observation that all this is satisfied if this is really the Poisson bracket between Z and S. But in the Poisson bracket, you have derivatives of functions if it's between two functions. But if it's a section, there is no natural derivative. You should have a connection. So it's a covariant derivative of S. And it should be flat, this connection, in order to satisfy the last requirement. So in other words, so we can have the hybrid quantum system where you have the classical dynamics on the classical background and quantum structure on the fibers. It's a Hermitian vector bundle over symplectic manifold with a Hermitian flat connection. So another physical word for this. It's a quantum system on a classical background. Mathematically, when you have an algebra that is finite dimensional over its center, such that every fiber is a matrix algebra, they are known as Azumaya algebras. So what we have here is a Poisson Azumaya algebras. In other words, on this big center of the algebra, we have a Poisson structure which acts by derivations of algebra. So now, more algebraically, a hybrid integrable system is the following. We have an associative algebra A, which is finite dimensional and simple over its center. We have a Poisson algebra structure on the center with the trivial Poisson center. This means that it's a symplectic. This spectrum center is a symplectic manifold. And this Poisson algebra acts by derivations of algebra. So then, in order to define the Hamiltonian dynamics, well, we simply have to lift the so we fix. Yes, so the Hamiltonian dynamics on M, the classical Hamiltonian dynamics, is simply defined by the choice of classical Hamiltonian. So then, since we have the flat connection that lifts the Poisson bracket to the whole algebra, so we can lift this Hamiltonian dynamics to the whole algebra A. But then this is not what we want. We want to have a little more. So hybrid quantum dynamics with the classical background. It's the following: we lift our Hamiltonian dynamics, but then we twist it by the action of quantum. So we fix an element of the algebra, and time dynamics now is the Poisson bracket with H plus the commutator with H1, which is the quantum. More generally, you can say the following: you have a derivation on the algebra of the algebra, which is mixed, so it acts on the center non-trivially, and it acts on the whole algebra according to this formula. So you can call such derivations split in the sense that we split it into two parts: the classical one and the quantum. I can imagine that there are non-split derivations, but let's not think about it. So this is the Heisenberg picture of the evolution. So you can say that quantum observables are self-adjoint elements of the algebra A, and it's the evolution of quantum observables. And then in the Schrödinger picture, the wave functions, they are sections of our vector bundle, and then the evolution is the following. The classical part of the evolution involves the Poisson brackets with the section, and then the quantum part, it's not a commutator, but it's a left action of our Hamiltonian on the sections. Now, one remark is that if we just have the evolution like this, it's not completely defines the Hamiltonian. You can add a scalar to the quantum. Nothing happens. Here, well, it does change the picture. So in some sense, this the Schrödinger picture is more fundamental. See. So now, so this was the hybrid quantum system. So now, what about integrability? So classical integrable system is when you have a Lagrangian vibration on the fiber, on your phase space. So you can think of this, of the base of this vibration as the values of n independent functions that Poisson commute. Then the level surfaces will be Lagrangian fibers, generic level surfaces. But that's a very special case when the base is a region in Rn. And I want to emphasize that typically there will be some singular points or singular subsets in B where the fiber is not Lagrangian, and these are very interesting points. But so that's the remark. And in general, of course, it doesn't have to be this way. Sort of more general picture is when you have, say, 1 million Poisson commuting Hamiltonians. From this 1 million, only 10 are, I mean, most of them are dependent, so there are many relations between them. And then this B will be algebraic variety in some huge dimensional space, but it will have dimension n. So, so I want to emphasize that it doesn't have to be all the time that these are just n independent functions on our menu. So then once you have this, or in a more general situation, you can always choose n independent functions. Then you have the multi-time evolution, and that's the feature of integrable systems. So there's a missing index j here. So this is the classical system, and then the hybrid integrable system is a lift of this classical multi-time evolution to our Hermitian vector bundle generated by some elements m1 n. These are the quantum Hamiltonians, and multi-time dynamics for such systems is, so here I use different letter m simply because there is no room for index 1 here. There is only room for index j. So so then the multi-time dynamics is given by this equation. So for each time there is a classical Hamiltonian, there is quantum Hamiltonian. Then of course this time dynamics should be compatible. So compatibility condition is this. If there would be no classical dynamics, then we wouldn't have this. Then this is the quantum integrability that quantum Hamiltonians should compute. If there is no quantum part, so then all we need is classical integrability, but that we already have. Okay, so then if we substitute, consider the time evolution of the section on the elements x of t. So let's denote this by psi t. So then, of course, for psi, we will have this system of differential equations. And so this is the essence of this hybrid integrable system, that on the space of times, so we have multi-time evolution, t1, tn. And on the space of times, this should be n. On the space of times, we have a flat connection defined by m operators. Okay. So yes, and then if you remember the classical Liouville theorem, what does it say? It says that multi-time flows, they form an affine coordinate system on level surfaces of it. So you can think of this as following. Geometrically, hybrid integrable dynamics means that we have this extra flat connection on the on each level surface. So geometrically, so we have the vibration. It's just a repetition of what I just said, and we have a flat connection on each level surface. And this flat connection is given by these elements in one. So this is the notion of the hybrid integrable system. It seems to me that it's very natural, even without further justification. But we can justify it even further. We can look at the deformation quantization of this algebra. So suppose that so we have an associative algebra A0. So we have the center of A0. Doesn't have to be finite dimensional over A0. It's just a completely general situation. Any associative algebra. Then let's assume that AH is a flat deformation of A0. So flat deformation means that in the appropriate topological sense, for each H, there is an isomorphism of vector spaces, AH and A0. So assume that as H goes to 0, this product, so we have this isomorphism. No, this is a typo. So what is meant here is the following: we take an element, we take two elements A and B from A0, and then using this isomorphism, we bring them to AH. Then this multiplication should be in AH, and then we apply phi again, bring it back to A. So the result is A star H B. So this star should be between A and B. It's the star. It's the induced star product on A0. So assume that it's expanding in the power series in H as H goes to 0. So typically, these deformation families in mathematical literature, they are formal deformations. Very rarely, non-formal deformations occur, like quantum groups, some other examples. So, then, very well-known fact that was observed, I don't know by whom, long time ago, definitely was used in a paper by De Concini and Katz about quantum groups and groups of unity, that this deformation, M1, the first term of this deformation, it induces the Poisson bracket on the center, and it also induces the Poisson action of the center on the whole algebra by derivations. So if we add to this picture the fact that A0 is finite dimensional center, fibers are simple, and then as a Poisson algebra, the center has a trivial Poisson center, then we have Poisson-Azumaya algebras or hybrid quantum systems. So there is nothing exotic in these structures. They appear all the time when we have a deformation family. So now, how about quantum integrable systems? These hybrid integrable systems. So let's assume that we have a family of associative algebras, and for each H, we have a family of elements of algebra A0 that starts with our classical integrables. Then first order term is something mk plus the second order. And assume that it's a commutative family. So in other words, we have a family of quantum commuting integrals such that as Planck constant goes to 0, for physicists it means that Planck constant is much less than typical scale of energies. So it's an abstraction of the physical understanding of the nature. But there were scales of energy. So in this case, we assume that the quantum Hamiltonians have this form, and then if you look at this commutativity condition, first order terms in H, they give exactly the what we told before, a hybrid integrable system of A0. So this hybrid integrable systems is not something exotic again. It's something that appears all the time when you have a deformation quantization of the algebra A0, and you have a quantum integrable system computing elements in this quantum deformation. Integrable deformation. So I was assuming that there are n commuting elements. In general, if you want to work in the most general mathematical framework, then you just assume that there is a maximal commutative subalgebra, and then it all goes the same. Okay, so we have a framework. We have the notion of hybrid integrability. Now let's look at examples. So the first example is the most natural quantum mechanical example. You can call it vector quantum mechanics. When the algebra of observables, I should have put H. It's the algebra of H differential operators, tensor product with the endomorphisms of V. So in this case, this Hermitian connection that I started with is trivial. So H differential operators means that locally in coordinates they look like minus IH dq. Of course, if you do the change of coordinates, these differential operators they will change, but they will retain the same structure. Okay. So now let's assume the following: that the Hamiltonian has the following structure. First, there is H0, formally self-adjoint operator times the identity X, identity E, minus some linear map in some matrix, and by n matrix that depends on derivatives plus terms of order H squared. So let's look at the semi-classical limit. So this is the quantum case. Now we want to extract the semi-classical asymptotic. So far there is no integrability. So let's look at the asymptotical behavior of the non-stationary Schrödinger equation with this semi-classical initial data. So then the answer is, turns out that it's well known in the literature on semi-classical analysis. So it's the sum over all trajectories connecting the cotangent bundle over Q, and the Lagrangian submanifold determined by this function f. So sum over all these classical trajectories, this Hessian, and then the Hamilton-Jacobi action on this trajectory, and then some function psi. Then, so explanation. So this is our cotangent bundle over Q. This is the this is the Lagrangian. No, sorry. This is the cotangent bundle Q. This is the origin. This is the Lagrangian determined by the function f. So it is one-dimensional case. It's just when the momentum is f prime of Q. It's a projectable Lagrangian to the zero section. And then there are classical trajectories that connect these two Lagrangians in time t. And then here they all end at the point Q, and here they end at some points Q alpha depends on Q and T. So S alpha is the value of the Hamilton-Jacobi function on these trajectories, plus the boundary term determined by F. Then psi functions, they are determined by solutions to this differential equation with the initial condition phi alpha. So you see, remember those differential equations for M operators that appeared in the Schrödinger picture of the hybrid systems. So now we have the differential equation determined by the first order term in quantum Hamiltonian. So So then, if we have n commuting Hamiltonian, so we have, so we want to describe now our quantum system is the the system of n particles, say, on a line. So then the semi-classical asymptotic of solutions to the corresponding non-stationary Schrödinger equation again is determined by solutions to this differential equation. So again, here it's the multi-time evolution. These are the classical trajectories connecting to Lagrangians, and these are the first order terms. So this hybrid integrable systems, again, they have natural space historically in this semi-classical analysis. Strangely enough, people in the semi-classical analysis, they studied quite a lot one-time evolution. Think about multi-time evolution. So then the next observation is, suppose that x star is a fixed point of the multi-time evolution. So then it's a fixed point. So fixed point means it's kind of the value just means that it's sitting over a very singular point in this base Pn that I was talking before. And this very singular point means that there is no Liouville torus over this point. The Liouville torus all shrunk into one point. So these affine coordinates T1, Tn that exist typically on a typical torus, they're all shrunk to a point. There are no coordinates, just this. So this is the kind of quantum integrable system on this very singular fiber. So this fiber is opposite to the fiber where there are Liouville coordinates. And so this is one of the source of pure quantum integrable systems. You start with the hybrid system, and then you find the fixed point, and then over this fixed point there is a quantum system. So now let's look at some examples, meaningful examples. So here is the spin Calogero-Moser in the style of Ikami and Wadati. This is the first instance to Polychronakas and so they first derived this system, but I think they didn't have the maybe they had two, but then Hikami and Wadati gave more integrals, so and they actually had n integrals, but they didn't prove the commutativity of all. So okay. So then eventually it was proven, and that's the integrable system. The first Hamiltonian is just the momentum. The second Hamiltonian is the Laplacian plus this interacting singular term, and this beta is just h. So then you see, if you look at the second Hamiltonian, you will discover that the first order term is just this permutation divided by sine squared, and the first order term is just 1. So as h goes to 0, you have the first order term, the classical Hamiltonian of the usual Calogero-Moser model without spin. All the spin part sits in the second. So if you take into account all high integrable systems, then you have the this hybrid integrable system with the quantum Hamiltonians 2, 3, and then what's most remarkable is that if it's a really should be called Calogero-Moser Sutherland system. So, if the interaction here is really sine, then there are fixed points. If it's a sine hyperbolic or there is no sine, which is the original Calogero-Moser version, so then there are no critical points. But for sine, there is a critical point like this. So it was. I don't remember the history, but as far as I understand, the first proof that it's a really multi-time fixed point for the multi-time flow. It's in our paper. So many facts about this were known. This point was called freezing point. It's definitely so. Anyway, so the nice fact is that if you specify the x to this point, p is equal to 0. Yeah, beta is 1 over h bar. If there is no spin, there are no spins, then the semi-classical limit is just you have a quantum integrable system that turns into classical system. Only if there are spins, then it's a trivial. Sorry? I said that beta is 1 over h. When I said when I denormalized Hamiltonians in such a way that h would be well, there is still a question. Yes, there is a parameter here. Oh. So, this is the Hamiltonian. This is M. So we have the this system with operators. Okay, and then the fixed point is p equals 0, q equals this, and yeah, if you evaluate the m operators at this critical point, then you can see that this is the Haldane-Shastry model for the second one, and immediately from this observation follows that um, commutativity with Hamiltonians, and also it follows that there is more kind of speech dynamics than just commutativity. So there is this differential equation. In particular, there is a question of how the system behaves in the vicinity of these critical points. For dynamical systems, that's a very typical question. Say if you have a fixed point of the evolution, how the system spins around this. So this is nothing about this. So the other example. So the other example is quantum spin chain. before I'll go to quantum speed chains, I want to justify the name M. So you can see that these equations, they are also known in integrable systems. So if you integrate classical integrable system using the Lux pair, then there is Lux operator L, and there is M operator that describes the time dynamics. So these are the M operators for higher dimensional flows. So if you add here the Lux operator, then the name M is fully justified. These are just M operators. So these hybrid integrable systems, strangely enough, the Hamiltonians are M operators of the classical algebra. So let's look at another example. So assume that we have a family of solutions to the Baxter equation. Consider the Yangian type algebra, which is generated by elements matrices acting in these spaces with the relations R. Typically, there are many other relations, but let's pay attention to this moment. Assume that the quantum R matrices are semi-classical. In other words, we expanded power series parameter H such that the first coefficients are classical R matrices, so that as a consequence of quantum Baxter equation, they should satisfy classical Baxter equation. And then we can consider the representations of this Yangian type algebra corresponding to spin chains, or in other words, tensor product representations that are obtained by the R matrices. So, these are the quantum spins. This one through Sn, it's an inhomogeneous quantum spin chain. So but then there is a special spin with this quantum space Q and with the G, and we consider Q as the, well, it's now we have two auxiliary spaces. P, it's really auxiliary space. That's why it's called A. We also have this other special space Q. So then, a well-known fact is that if you take trace of this quantum monodromy matrix, you will get transfer matrices that commute, and then if we consider the semi-classical limit when the spins of this quantum spin chain, in other words, representations, say highest weight representations, they go to infinity, and that's representation theoretically. It means that it's the limit when endomorphisms of your representation becomes the functions of the corresponding coadjoint form. So that's what's written here. So in this limit, the quantum transfer matrix becomes the classical transfer matrix times the identity operator in space U. And the first coefficient is, so that's the classical. Here L are classical Lux operators. Then the next coefficient is given by this formula, and these are simply the M operators corresponding to for this classical speech. This, I don't remember, it's either Sklenin or Karipin situation, one of the very important observations. Because, see, these are matrices. They go to classical L operators in zero order. These are matrices. So the space U remains quantum. So it becomes 1 plus classical. One we already accounted for, that's classical. So first order is use this trace. So now you can sort of play with various games with how to extract quantum Hamiltonians. One of the possibilities is that you choose special values of the spectral parameter u. For each value of the spectral parameter u, the Yo Hamiltonian is simply the corresponding classical constant. So this way you enumerate times by values of spectral parameter. And of course, there are infinitely many of those, but if the system is finite dimensional, then only finitely many are independent. So then we have the well-known property of M operators that for different flows they commute. That's exactly the hybrid system. Talking about then an open question. Say, suppose that you have a classical spin chain, just discrete Landau-Lifshitz classical spin chain. Question: are there any fixed points? The answer is not. In general, the historically the development of integrable systems was almost entirely focused on the integrable dynamics of generic fluidal fibers. Now you can see that the extreme case is also very interesting. The fiber is extremely non-generic, but as singular as possible. Now, of course, if there is some kind of intermediate situation, if the fiber over this point is, if X belongs to not extreme fiber when it's just one point, but some low dimension, then well, you will have some of them will compute, and some of them will still be some kind of flat connection. So they will sometimes. So this sort of completely new universe, going from some sense mathematically more interesting algebraic geometry. Nobody studies regular points. So singular points are interesting. Here is the kind of dynamical justification to the fact that singular points are very interesting. So another example. So with Bazhanov and Babenko, we described it in 1995. So we studied discrete signed-order model of unity. So think of this as quantum groups and roots of unity instead of the continuing cuts. And the reason for this study was we wanted to explain chiral Potts model as part of the did. So the conclusion was that you have this discrete time, discrete signed-order dynamics on the lattice. But then there are very special initial conditions when the dynamics is periodic. It goes from layer to layer, repeating itself. That's the analog of fixed point. And the dynamics at this fixed point, the quantum transfer matrices at this fixed point, are exactly the chiral Potts. So, but somehow then the analysis became extremely technical. We all went in different directions. Bazhanov Smolotchik was, yeah, so Kashak, yeah. So they opened chapter theories. Babenko discrete geometry, else, and basically the subject was cool. So that's a very interesting subject, and I think now we have a new look at it. This is a separate. Nicolai, happy birthday.
Okay, thank you for your talk, and we have uh, time for a few questions.
Oh yes, I forgot to say this.
His son will be age. That's it.
I
We have
forgot.
such a thing the last
Yes, yes,
2000.
yes. I forgot to say about this. Uh, this so in the paper there will be a last section, and that's it's exactly what it's. Basically two words. So you have the in case of cosmological equation. Say if you have n spins, you consider n minus one. One of them to be classical, one of them quantum. But I didn't know. But that's a long story. I had so no, that's so in this case you well you know so, the classical part will be the kind of goddamn dynamics, and the quantum part will be the Schlesinger equations for that. This story works. The goal of what? No, no, no. I mean, yeah. If you say that no, this story is well known. No, no, no. These are not lattice points. These are fixed. I wouldn't call them lattice points. These are fixed points. Okay. Yes. 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 No, what can be obtained by a certain union is this. So you have computing differential operators. On each there is no discretization. Uh, no, no, no. This I completely against. It's not. It has nothing to do with discretization. It's, the words may have some meaning. So in this case, discretization has no. It's a special fixed point. It looks like it is. Yeah, the main point here is the following. You have this just a second. So I understand your question. So you have this flat connection. Each dual terms, each regular and single. Regular you have n times yeah, and then this most singular. Uh, The Liouville torus is just one, and that's this. This system. This is a separate solution. It's a separate contribution that there are. If you take Calogero-Moser without signs, it's hyperbolic signs. For this particular Calogero, there are no. As Liashyk said that if you add x squared, it's example that follows. So first you observe this, right? Then you observe that if you have a fixed, then this ddt act on n is 0 because it's fixed. Yes. So we have activity. You know, it's like this. Yes. Oh, so yes. In the limit as h goes to 0, this part plus the scalar for the interaction, they together form the classical Calogero-Moser, which acts trivially. And it drives the classical. The first coefficient gives you the this quantum performance. Yes, and then you take H3. Yes, you have something more complicated. H4, you'll have something even more complicated with force momenta and horrible problem.
Let's probably continue it on a coffee break.
One. Yes. 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 Okay. I'll explain.
Okay, thank you for your talk again. We have short break now, and we continue with the second talk before lunch.